Thank you very much. So in this work, I will tell you how we will be preparing for the aliens that Amit just mentioned in the previous talk. If they want us to obfuscate AES and then complete running it in 5 years, we have to start early on. Be ready for this. So in this work, I will tell you about some efforts that we had to actually try starting to implement some of these primitives that relate to obfuscation and will be useful to eventually have a full-blown obfuscation construction. So in my talk, I have to warn you that I will repeat several things that Amit already mentioned, but if you haven't seen them before, this will be just to reconfirm your understanding of that issue. So let me start again with the definition of obfuscation and why do we want to obfuscate something. So if we have a piece of code, we would like to obfuscate it in order to make it unintelligible for somebody who gets our code, and then at the same time maintain its functionality. So we want to be able to take a program, obfuscate it, give it to somebody so he doesn't understand what our program is doing, but yet be able to use it and run it on any input that he or she might want. So why would we want to do this? Well, I mean, in general, this approach of obfuscation is allowing us to hide secrets in software. So this might be because we have proprietary algorithms that we want to hide from the people who will be using them. We might want to be able to issue software patches without pointing directly to the vulnerability in our programs. Or maybe we have applications such as malware detection, where maybe our application already has to have some hard-coded signatures of the malicious software that we'll be looking for, and really hiding them is crucial for the proper functionality of our programs. So there are many applications of obfuscation, and I'm not going to motivate any further for you why we want to use obfuscation. So now that we have defined what is the functionality that we want from obfuscation, let me have a look at this word unintelligible and what it means. Amit already mentioned that in one of his works that introduced the notion of obfuscation, they also started defining what are the notions of security that we might want from obfuscation. So the strongest notion of security that he mentioned is this virtual black box security, which essentially captures our intuition of what obfuscation should be. That really an obfuscation that takes the real description of the functionality that we want to hide should be indistinguishable from an obfuscation that has a oracle access to something that is just able to give input-output pairs that correspond to the work of this functionality. So this is a great definition of security, and ideally this is what we would want from the security of obfuscation. The only bad news is that in the same work, the authors show that this notion of security is impossible, and you already heard in Amit that it's impossible with some contrived example, but it's still, as a result, is impossible. So the next thing that we look at is the notion of indistinguishability of obfuscation, which weakens the security guarantees that we can have from an obfuscation to the setup where the only thing we are able to hide is if we have two circuits that we have exactly equivalent behavior on all inputs. Then if we take these two circuits implementing the same functionality, we want to say that the obfuscations of these two circuits are indistinguishable. And this notion, also in another work, was shown to be kind of the best possible obfuscation that we can be hoping for. And the other good news about this construction is that we don't know impossibility result, and in fact, by now we have several candidate constructions for indistinguishability obfuscation, which started with our work, and by now there are many, many other constructions. So this is how we define the security of obfuscation. And next I want to draw your attention to another primitive that turned out to be very closely related to obfuscation. And I would like to give you a glimpse of how this is related and why we should care about this primitive. And this would also be something that we will be considering in our implementation efforts. So this is the notion of functional encryption, which was introduced by Sakai and others in 2005. And this notion encryption kind of tries to introduce new functionality in the notion of encryption schemes. We want to be able to construct keys that, rather than enabling us to open completely an encrypted message, would only enable us to extract certain information about this message. More specifically, we would be able to evaluate only a particular function of the encrypted message. So if you want to think about an example, and if Alice has her driving license, but she doesn't like to hand it to everybody her driving license, maybe she would like to encrypt her driving license. And now, when she goes to the bar, the only thing that she wants the bartender to be able to infer about her is whether she is above 21, if you're in the US. So we would like the bartender to have a key, a decryption key that takes the ciphertext of Alice's driving license, and the only thing that he is able to learn is whether she is over 21. On the other hand, if we have a policeman that stops Alice and wants to figure out whether she's allowed to drive the vehicle that she has, maybe this policeman will have only a decryption key that allows him to understand what is the driving category in her license. So this is the type of functionality that functional encryption will enable us to have. And let's look a little bit more into what functional encryption will be giving us, because there are many different flavors of functional encryption, I would say. So I'll try to give you an idea what are the different variations, and then we will see how some of them will be useful also for constructing obfuscation. So a functional encryption, we first have a setup algorithm that allows us to generate the keys for this encryption scheme. So we'll have an encryption key which will allow us to construct ciphertext, and then we'll have this master secret key associated with the scheme. Now, we have also an algorithm that allows us to generate these different decryption keys that are associated with particular functions. So if we're given the master secret key of the encryption scheme, then we can run this key generation and obtain a secret decryption key that's associated with only some particular function f. And we will see during decryption how this function f will be used. Then we can also encrypt ciphertext in functional encryption, taking the encryption key for the scheme and the message that we want to encrypt. And finally, what happens when we have a decryption in this setting of functional encryption is that we, given the decryption key associated with the function f, and then a ciphertext that's encrypting a message n, the only thing that we're able to learn is the evaluation of this function f on the message, and nothing more. So this is kind of the main, the bare bones of a functional encryption scheme. And now I mentioned that we have different flavors of functional encryption. So for example, one thing that we can ask about the functional encryption is whether we need to be able to publicly encrypt, whether we want this to be public encryption or whether we want to be a secret encryption. So we have two types of encryption scheme here, and if we are in the setting of private key, then our encryption scheme is the same as our master secret key for the scheme. Next, we can also ask whether this decryption key that we are releasing for the functional encryption is hiding the functionality that we're embedding in it. So if we're given S case of f, whether we learn what's the function f or whether this function is hidden. Being able to get the function hidden will give us much stronger properties for functional encryption. And then the last flavor of functional encryption that I want to mention, which I will be also focusing in our implementation efforts, is the notion for multi-input functional encryption. So what I said so far is that we will be able to decrypt a single ciphertext with this decryption key. Now what I will be asking for is that we can encrypt messages for different slots in the encryption scheme, and then we would like to be able to decrypt using the decryption key for the FE scheme multiple ciphertexts. So now here we'll be evaluating a multi-input function, and the different inputs will be coming from different ciphertexts which were generated independently, and they don't share any randomness or if it's randomness or anything of that sort. So this is kind of the land of functional encryption that we have now. And I mentioned to you that functional encryption will be very useful in order to construct obfuscation. And I want to just show you two of the relations that we know that are kind of simple to see. So the first one is, if you think about function hiding, public key functional encryption. So this is already an obfuscation, right? So we are able to give you a decryption key where the function is hidden, and then at the same time you can publicly encrypt messages. So what would be our obfuscation? This would be just the decryption key, which is already hiding the function. And then in order to evaluate the obfuscation, we can encrypt any input on which we want to evaluate it, and then we can run the decryption. So this is very simple. So if we manage ever to get a functional hiding in the public key setting for functional encryption, then we're very far on the way for obfuscation. So the second example that I wanted to show you is related to the notion of multi-input functional encryption, that it actually also implies obfuscation. And this was shown in the works of Anand and Jane. So in this construction, we are able to construct an obfuscation that will be able to execute on inputs of length n bits. And for this, we will be using multi-input functional encryption that allows us to have n+1 encryption slots. So how can we do this? Well, the obfuscation for our function will consist of the following things. So we will give a decryption key for the multi-input functional encryption. Note that here I'm not requiring any hiding property from the decryption key. So we will give a decryption key for the universal circuit. So a universal circuit takes as input both the description of the function that we'll be evaluating, as well as the inputs on which we will be evaluating the function. And now, together with this decryption key, we will give an encryption in the 0 slot, and this will be an encryption of the actual function that we want to obfuscate. And then for every other slot, we will give 2 encryptions, an encryption of the bit 0 and an encryption of the bit 1. So total n+1 slots. The first one is single encryption, all the others 2 encryptions. So now if we have all of these, we can actually also evaluate this function f on any input that we want. So how would that happen? If we want to evaluate the function on n bits, so m1 to mn, what we will do is we will run the decryption with this key for the universal circuit, with the encryption of the function that we have, and then we will be selecting for each slot the encryption corresponding to the bits that we have. So if m1 was 0, then here we will select the encryption of the bit 0. So we just select from these pairs the corresponding input bits, and when we run the decryption on this function and these encryptions of the bits, then the result by the definition of the multi-input functional encryption will be the evaluation of f on all of these input bits. So this is another beautiful result that shows us how to actually get obfuscation from multi-input functional encryption. And so the landscape of what are the connections between functional encryption and obfuscation has been quite enriched recently. So these are the 2 connections that I already showed you in the previous slide. But by now we have much stronger results, which I won't be describing to you, but we know how to build functional encryption actually starting from public key functional encryption with no function hiding. Of course, we have to have a bag of tricks that are more complicated constructions than what I showed you. And also a very, very recent work shows us that private key functional encryption, single input, is also sufficient in order to construct obfuscation. All of these things, what they are telling us is that if we want to think about the construction of obfuscation, we might as well think about construction for functional encryption. Okay, so we had all these wonderful results about connection between functional encryption and obfuscation. different candidates for construction for both of them. So at this point I was sitting and I was thinking, can we implement any of this? Is this, like, we have wonderful theoretical work, we have great motivations for why we would want to have functional encryption obfuscation, so is this ever going to be possible to implement? So I was dreaming of this, and then when I was dreaming, I had this like nightmare of, like, we know FHE, the efficiency of FHE is like scary, and this is scary, but when you start dreaming about multilinear maps efficiency, it gets even scarier. Right? It's the efficiency of the current candidate construction is terrifying, and I didn't know how we can do this, but then you gather a team of amazing people who actually venture to try to implement this construction and see what the efficiency of this construction currently offer us. So, well, the summary of our results, which will appear in a paper in CCS in October, are the following. So we construct and implement a framework for prototyping applications that are using multilinear maps and branching programs. So our hope is that this framework will be available for everyone who wants to experiment and try out their new multilinear map schemes or new constructions from multilinear maps. And this will give a set of useful tools that you don't have to re-implement every single piece in this construction, but you can just plug and play with our framework. So our framework has a compiler that starts with a description of your program in a language called Cryptol, and then it automatically generates this matrix branching program that Amit was mentioning in his talk, which is used in many of the constructions for obfuscation and functional encryption. So after this compiler, we have also API library with different multilinear map constructions. So currently our implementation includes the GGH Lite construction and also a variant of the COT13 multilinear maps that kind of remove the capability for public encoding. Also, we have an application, several applications implemented in our construction. So we have a construction for multi-input functional encryptions with two main instantiations. One of them is order reading encryption, and the other one is 3DNF formulas. And then we also have a general obfuscation construction based on branching programs, and we in particular looked for evaluation at the obfuscation for point function. And in this, together with this framework and the different pieces that we have implemented so far, we kind of run several tests to see what is the current efficiency over it. So what is the architecture for our system? So we have a function specification layer, and in this layer, we have the crypto language, which is an existing language, so you can write down your programs in crypto, and then plug it in our framework. Then we have this function representation compiler, cryptfms, I don't know how to read it. So this is the compiler that takes your crypto program and will spit out a matrix branching program. Then we have the application layer where you can plug in and implement new constructions based on multilinear maps. So currently our application layer offers multi-input functional encryption and obfuscation, branching program-based obfuscation, just because there are also constructions that are directly using circuits. We are hoping we'll soon have additions for those too. And then we have the API that's implementing multilinear maps, but who knows, maybe we will come up with an obfuscation construction that doesn't need multilinear maps, that we will use some other tool that we can add here to the API. So currently, if you have a program, you write your program in Cryptol, this Cryptol goes through our compiler, it invokes whatever application we want to be implementing, and then this application is using underneath the library for multilinear maps. So, as I mentioned, Cryptol is an existing language for describing cryptographic algorithms. I think it's used widely in the intelligence community. It has some nice properties that you can obtain from the executable formats, and also you can prove some formal properties of your specifications, some equivalence between different specifications, and you can generate implementations in other languages starting from crypto. So this is one of the reasons that we chose crypto as our function specification layer. Then once you write your function in crypto, you go to our compiler from crypto that goes through a minimal finite state machine, which is after this converted to a matrix branching program. At this layer, we have several optimizations that look at the finite state machine and track reachable states, and also in the actual matrix branching program of optimizations that are specific to your application. So I will next describe some of the optimizations that we are looking at. And for this, I will have to remind you of what are branching programs, although you already saw in Amit's talk, but let's go over it again. So branching programs, which were introduced by Barrington, are computational model in which we specify our computation with this, let's say, triples. So you have a branching program of length m that takes n input bits, and it's defined by these pairs of matrices, and then in addition you have a function that tells you for each position in your branching program which input bits you have to be looking at. So if you want to evaluate a branching program for a function f, what you will do is you will select in each position the matrix that corresponds to the value of the input bit. You will multiply all the selected matrices from the branching program, and then you will check whether the result is the identity matrix. And if so, you will output 1, and otherwise you will output 0. So let's look at this same thing, but in pictures, and an example, which is much more clear always. So if we have a branching program of length 9 that has 4 input bits, so now we want to evaluate it, and let's say that the function that maps positions in branching program to input bits says that the first input bit determines the 3rd, the 6th, and the 9th slot. So if we have 0 as first input bit, we just select the matrices that correspond to the 0 in these locations. Then if we have 1 in the second position, again we select the corresponding matrices in the corresponding slots of the branching program, and we keep on doing this for the rest of the input bits. Once we have selected for each position in the branching program one matrix, we just take the sequence of matrices, multiply them, and we check whether the output is 1 or not. It's the identity. Okay, so how do we construct branching programs, matrix branching programs, if we just have our crypto's specification? So one way was the famous theorem of Barrington, which tells us how to convert any circuit to a matrix branching program. The bad part of this is that the size of the matrix branching program becomes exponential in the depth of it. So most likely this would not be the most efficient way. The other approach, as Amit mentioned, is going to finite state automaton to the matrix branching program. So you can just take the finite state machine that represents your computation, and this is what Cryptol is good at compiling down to a finite state machine. And then you can specify the matrices that correspond to the transitions in your finite state automaton. So you can figure out which are the transitions that depend on your first input bit, and then you can write the transition matrices which correspond to whether this input bit is 0 or input bit is 1. And you can keep on doing this for all of the input bits of your program. So this is kind of the main idea of transitioning from finite state automaton to matrix branching programs, which we will be using in our implementation. So some optimization that we will be looking for is condensing the input representation. So basically you can use a larger set of transition symbols in your finite state automaton, which would result in fewer transitions but then more states. So if we have this little finite state automaton where each transition is determined by a single bit, we can also rewrite it looking at 2 bits at a time. So now we will increase the number of states in our finite state automaton, but before, if we had to have as many transitions as the number of input bits, now we cut this by 2. our compiler, we will be looking for such a possible, like, what is the trade-off and what are the benefits of each. We will also look at a different type of optimization, which is matrix pre-multiplication. So for some applications, mainly for the multi-input functional encryption, it might be the case that certain positions in the branching program are fixed to particular values. And in this case, if you know that in these two positions your values will be fixed to 1 and 0, you might as well pre-multiply the matrices and not have to do this at evaluation time when it's much more expensive. You can also think about reducing the dimensions in your matrix branching program, and this is mostly based on the observation that not all transitions affect all of the states in the finite state automaton. For example, maybe your first input bit is always restricted to start at state 0 or 1, so we can really ignore the description that's related for the other states. Or maybe you know that your transition never goes to some of the states, you transition only to a subset of the possible states. So you can start reducing the dimensions of your matrices, and again, you have to be careful because some of these optimizations are not compatible with each other.
The matrices should be invertible, no?
So they're extensions of the main construction where you actually are able to do obfuscation not using regular matrices. So we are kind of putting in all of the most recent constructions for branching program obfuscation. Okay, so this was the part of our compiler. Next, we'll have our applications, which include obfuscation for point function obfuscation and multi-input functional encryption. So for the obfuscation, as I mentioned, we will be looking at these matrix branching programs, and we know how they work by now. So the next step, as Amit was mentioning, is to have this re-randomization procedure, which was introduced by Kilian, where what you basically do is you select a few matrices, invertible matrices R0 to Rn, and what you do is you kind of attach them on both sides of your initial matrices in the branching program. So you multiply by the inverse and by the next randomizing branching program. And what this enforces is it enforces the order in which you can be multiplying your branching program. And also, as in the work of Kilian, this has some nice security properties, which of course will not be sufficient for obfuscation, and we will need to apply on top of this some encoding techniques, which will use the notion of the primitive multilinear maps, which I will remind you again. A multilinear map gives you a way to encode an element with respect to some set S, and then it gives you some nice properties, algebraic properties on the encoding, which is hiding the element. So you can add two encodings that are at the same level, or you can multiply two encodings at different levels where you also change the level of the encoding of your code. And of course, you have to have something crucial for the functionality for multilinear maps, which is called a zero test parameter. This zero test parameter is associated with a particular level, and then it allows you to check whether the encoding at that level is zero or not. The state of the construction of multilinear maps is a very turbulent one. We have several candidates that have been attacked, and there are various attacks for this multilinear map construction, as well as some of the applications from them. I have to warn you that some of our instantiations that are in the framework by now have some attacks, but it's still, I think it's still interesting if you are coming from the practical point of view to see, to actually use and attack them. And in fact, on the RUM session in crypto, there will be a challenge announced which will give out some of the multi-input functional encryption and the obfuscation we obtained, and see how well people can actually apply practical attacks on those. So anyway, so we will be using these multilinear maps to encode the branching programs, and as Amit mentioned, we will have this notion of straddling sets, which enforces the order in which things will be multiplied. You can think about these straddling sets as if you have a huge set which represents your zero testing level, and then you basically partition it in different ways for the different evaluations. I'm not going to go into details. So we encode everything with this multilinear map and the zero test. So now that we have this construction for obfuscation, we can transition also to a construction of multi-input function encryption. So for the purposes of this implementation, we considered private key multi-input functional encryption that allows you to give a single decryption key. So once we think about a single decryption key, we can just make it part of the setup of the generation of parameters for the multi-input functional encryption. So here we give out the master secret key, which we will use for encryption, and we give out the secret key associated with the particular function. Then we can encrypt for different slots, and we can do the regular decryption. How can you construct this from the branching program that we have? So let's say we have this like little short branching program which describes the computation of the function f. Since we have a single key, there is a single branching program. Well, I mean, we can consider we know that we will be partitioning the input. Let's say that our input will be partitioned in parts. So we can look at the positions in the branching program which are determined by the inputs that should be all gathered in the first ciphertext, and we can consider what are the positions in the branching program determined by the second ciphertext. So we can say that the encryption for the first slot will consist from the branching program, the encoded branching program matrices that coincide with the value that we're encrypting. So here, if we're encrypting 0 and 1, we are giving out the matrices corresponding to 0 and 1 in the particular positions. And we can define in the same way the encryption for the second slot. We'll be selecting the corresponding matrices for those slots that correspond to the input values. However, this, as it is not secure because you can apply type of mix and match attacks. So here, if you're given an encryption for the first slot for 0, 1 and for 1, 0, you should not be able to obtain an encryption for 1, 1. However, what we have done so far, there is nothing to prevent us to do this. So we can just mix and match from the different ciphertexts. And this idea makes me think of multi-input functional encryption as a type of a constrained obfuscation, right? If you had the regular obfuscation, you are allowing your party to evaluate on every single possible input. And this mix and match in the context of obfuscation is just the regular functionality. Now here we will be restricting our evaluator to be using only what's given in a ciphertext as input for evaluation. So for this, we developed some technique that's called exclusive partition families, which basically allow you to generate an exponential, a family of exponential size for partitioning for the zero testing level. I don't have time to go in details for this, but basically the idea is that once you have this exponential size family for partitions of the zero testing level, you can, at each encryption, you can choose at randomly one of these partitions and use them for the encryption. So this kind of multi-input functional encryption, one useful instantiation is called order revealing encryption. So the idea here is that you want to be able to perform comparisons on ciphertexts. So you want to be able to basically sort. If you're given a number of encryption, you want to be able to sort them. And comparison has a very simple instantiation, and as a finite state automaton, you have 4 states that show whether the first input is larger or the second. And then moving through the bits of the 2 inputs, you can kind of see the transition between the different states. So essentially, going through this automaton that computes comparison, and I'm skipping forward because I see my time. We can have this finite state automaton, which we know, and I described to you how we will convert it to my matrix branching program, and we can plug it into the multi-input functional encryption construction. We also had one more instantiation of MIFE, which is basically 3 DNF formulas that are this sort, of this form. It's in this one, we looked at it because it kind of resembles the types function, which has been very useful in different contexts, including construction for witness encryption and obfuscation. It some particular applications, you can define a fraud detection scenario where this function would be useful. So this was another instantiation of multi-input functional encryption that we implemented. And then finally, the final component of our layer is the multilinear map instantiation. So we had two instantiations. The first one is the GGH Lite, which is multilinear maps based on ideal lattices. This is the particular construction we were looking at is a modification of the original construction of GGH, which was introduced by Albert et al. Our implementation started from their implementation, and then we did some extended capabilities in terms of the encodings levels that I mentioned that are necessary for the obfuscation and the MIFE construction. We did something that we needed for disk I/O for the parameters of the scheme. We followed the parameter setting that was prescribed by the authors. I have to mention that there are existing attacks for this in the context both of multi-input functional encryption and obfuscation, where in obfuscation you really have to look at contrived programs. For the multi-input functional encryption are more explicit, and this is the annihilation paper that Amit and his co-authors will present here at Crypto. Still, this was kind of developing in parallel with us. It will be interesting to see whether we can apply this directly on our challenge as well. The second instantiation of multilinear maps, we looked at the CLT construction, which are multilinear maps over the integers. We started from the CLT 13, removing public randomization parameters. We did also some speedup for the encodings and the evaluation. We did the same things that we did for the disk I/O. In the CLT, we'll be looking more carefully into the parameters, since often the asymptotic evaluation are not very tight, so we'll be looking how much we can optimize there. And so there are existing attacks on the CLT multilinear maps. None of them I think are directly applicable for our application for direct breaks, which doesn't mean that we won't have an extension of this attacks to our applications too. But let me jump to some of the numbers since I have only a few minutes. So we evaluated multilinear maps, the efficiency of multilinear maps, order revealing encryption, 3 DNFs, and point function obfuscation. So here is what the size of multilinear map encodings look like. This blue lines are GGH Lite, and these are the different security parameter levels, so 40 and 80. And this is the CLT. The red lines are the CLT parameters for 40 and 80. This kappa here is the degree of multilinearity that the multilinear map can handle, like how many multiplication you can do on the encodings. So you see that the size of the encodings are in the form of megabytes. Really, if you look at the high security level of 80-bit security, then the size is like a couple of megabytes. And if you want to construct from multilinear maps order revealing ciphertext, this is what happens with the size for the order revealing encryption. So here the x-axis is the base for our integer that we use, which kind of affects the finite state machine that we have and the matrix branching program representation. These are the different optimizations that we have. One is the dimension reduction, one is the matrix pre-multiplication, which are not compatible always with each other. And the size of the integers that we were looking at were, the domain was 10 to the 12, which was also... What security parameter? What is the security parameter for this? These are, I think, these are 40-bit, yes, 40-bit security. So this is what happens with the size. So the size of a ciphertext includes all the encodings for all the entries in the matrix branching programs. So here we are of the orders of gigabytes. So this is just a ciphertext representing a single integer that we would later be able to compare with the multi-input functional encryption. We also looked at what happens with the size of the ciphertext when you change the size of the domain, because if your domain is too small, there is like a basic construction that kind of more or less hardcore, like gives you all the comparisons explicitly listed in your ciphertext already. So you have to really compare with this basic construction and see at what point using order revealing construction with the size of these encodings becomes more efficient in terms of ciphertext size than this trivial construction. So that also motivated our choice of 10 to the 12 because this is where the size of the ciphertext from based on multilinear maps becomes more efficient than the basic construction. And in terms of the final one is the obfuscation size. So we have this obfuscation for point function encryption. So we really here wanted to look at realistic security parameters because otherwise the breaking the obfuscation for point obfuscation is more of a exhaustive brute force attack on the hidden points rather than the obfuscation scheme itself. So here again the size of the obfuscation is in gigabytes, and we have the same dependence in terms of the two multilinear maps, using the two different multilinear maps and the security parameters. And one last thing that I will show since my time is out is the actual runtimes. So everything so far that I was showing you was size of ciphertext. Now if you care about actually evaluating it, so encryption time, if you're happy with 40-bit security, runs in minutes, where the minutes for CLP are smaller than the minutes for GTH. If you want to go to 80-bit security, now you are looking more of the order of hours. This is the encryption time. The evaluation time for decryption and comparison is much faster. Here we have seconds, here we have minutes. We have a lot of a major consumption of RAM when we do all of these operations because we need a lot of intermediate state. And here is the table that does the same thing for the point obfuscation. So the obfuscation here is of the order of a couple of hours. Only with CLT we managed to run obfuscation with 80-bit security. Evaluation time is again much faster than the obfuscation, which in some context this is the only thing that will matter because this is all pre-computation. And again, if in order to store this obfuscation you will need several gigabytes and a lot of RAM. Yeah.
What sort of processor is this?
Okay, so this was run on the Google Compute Engine. So we use 32-core Intel Haswell CPU, 208 gigabytes RAM, and 500 gigs disk space. And with this I want to thank you. We give you this framework. Please go and play with it, experiment with your constructions. It's very modular. You can use only some of the parts of this framework. And we also give you some evaluation time so you can compare with them or you can break them. So thanks again.
Are there any questions?
Yeah, so these runtimes and evaluation times, do they include reading these hundreds of gigs of keys?
Yes. Yeah. It includes I/O. It includes input-output reading. Like I/O is in a different way.
Okay.
Yeah.
So could you give any criterion for a program to be more efficiently implemented on obfuscating?
Well, I mean, if you have an efficient finite state machine for your program, that would be definitely better. But if you're going through the branching programs, otherwise you would really want to go through the circuit obfuscation, where maybe to going for a PRS. Yeah, so everything I presented is going through the branching program paradigm. There is a paradigm for obfuscation going directly through circuits. So there will be functions that are more efficient than branching programs. There will be ones that are more efficient than circuits. For this one, really also the kernel helps you because it's a language that has a lot of machinery that actually optimizes your branching programs, and our extensions